All right, welcome back, everybody. All right, looks like there's a little bit more space in here. It's also hotter, though. So today we're going to revisit least squares from the geometric perspective. And we're going to talk about a few concepts that showed up under the hood there that we didn't talk about explicitly. Today we're going to talk about them explicitly. They're general concepts that show up beyond the context of least squares, but are very helpful to understand in this context because we know a little bit about it. And we're going to see them again as we start talking about things like the singular value decomposition next week. So recall that we had observations of training data that looked like xi, yi pairs for I equals 1 to n, where xi would be a vector of length p corresponding to p different features for every example. And the running example we've been thinking about is, for instance, taking pictures of people and trying to predict whether that person is smiling or not. And the features for, say, the eye photograph would be things like distances from the corner of the eye to the corner of the mouth, etc. Okay, so we formed a vector of labels y, which was y1, y2, all the way to yn. And we formed a feature matrix X that had all of these feature vectors in it. So x1 transpose was the first row, and x2 transpose was the second row, all the way down to xn transpose as the last row. And this matrix was an n by p matrix. Okay, so then what we did is we said that what we wanted to do was to find some vector y hat that could be written as xw such that somehow this vector y hat was as close as possible to the original labels y, if we think about the length of that vector, or in this Euclidean norm context. So we want to make sure that that is as small as possible. And then another way of phrasing this is we said, let's let capital X1, capital X2 through capital XP be the p columns of X. So this would correspond to, so each one of these is a length n vector. So this would say, okay, for the distance, say, from the outer corner of the eye to the corner of the mouth, we've got that measurement for all n of our different samples, and that would be x1. And then the width of the mouth, we've got that measurement for all n of our samples. That would be the column x2. And the idea is that y hat, this new vector of predicted labels that we're trying to come up with, can be written as a weighted sum of those columns. So w1 x1 plus w2 x2 all the way to wp xp. Okay, so this is the basic least squares framework that we've been thinking about. And when we drew a geometric picture of this a week ago maybe, it looked something like this. So we started by drawing this hyperplane. And we said that this was the span of the columns of X. And for today, I'm going to write that with a little calligraphic X here. And that just represents all the points in this plane. And we said what this means is that this is the set of all possible vectors v that are of length n that can be written as v equals w1 x1 all the way to wp xp for some set of weights w1, w2 all the way to wp. Okay, so this hyperplane that I'm drawing here corresponds to all the different vectors that could possibly be y hat. So we're going to choose a specific y hat. We're going to choose the y hat that's as close as possible to y. But these are the choices that we have when we're choosing x hat, because, I'm sorry, y hat, because we said y hat has to be a weighted sum of the columns of x. And what we mean by that is it has to be possible to write y hat in this form. So this plane here is that space. Then what we did is we drew, we said imagine this is the origin, and here I've got x1, and here I have x2, so I've got these two different columns of x. And what I observe as my observed labels is some other vector y. And unlike the x's, y does not live in this hyperplane. And what we want to do is we want to find the point inside this plane that is as close as possible to y. And that's what we're going to call y hat. And we draw it like this in this plane because y hat has this form here. Okay, so we talked about this a week ago. And now what I want to do is I want to provide a little bit of additional context here. So the first thing, I'm going to introduce some vocabulary as we go. So the first thing we're going to talk about is that X is something called a subspace. So we're going to talk some about subspaces today. This is an example of a subspace, but we're going to talk about more about subspaces. If the columns of X are linearly independent, so that means that somehow they're not representing the same information. So we don't have like two copies of the same column, for instance. Then those columns form a basis for the subspace. So we're going to talk about what a basis is, and we're going to talk about how to represent a basis and how to think about basis and different properties that a basis might have. And then, well, I guess I'm out of room here. The final thing that we'll discuss is that y hat is the projection of our original label vector y onto x. And maybe from the picture that kind of makes sense, right? From some perspective, you could imagine a light shining down and casting a shadow, and y hat is the shadow of y on this subspace or plane that we've written down here. But we're going to think more formally about projections and projection matrices. So that's the agenda for today. We're going to think about these three concepts: subspaces, bases, and projections. We're going to use this notion of least squares as a motivating example, but these ideas are all going to show up again and again throughout the rest of the quarter. Okay, any questions so far? All right, so first we're going to talk about subspaces. Okay, so you could start by considering all points that are in Rn. So all length n vectors of real numbers. A subspace is a subset of these points that just satisfy some key properties. So in particular, if I've got 2 points, x and y, that are inside the subspace, I'm just going to write the subspace using a curly S here. So if x and y are 2 points that are in the subspace, then their weighted sum, ax plus by, also is in the subspace for any weights a and b. Okay, so this has to be true for a subspace. It's a set of points, and all the points that are in the subspace, well, all of their linear combinations or all of their weighted sums are also in the subspace. All right, so that sounds very abstract. So we're going to look at a bunch of examples now, unless there are any questions right off the bat. Face is too far away. Okay. So first, let's just do a more geometric example. So in this case, n is equal to 3, because I'm going to be able to draw it. And I'm going to start off by drawing my 3D axes. How do I do this? So this is I'm going to call that the x1 axis, the x2 axis, and the x3 axis. And my subspace is going to be the set of all points x that are three-dimensional vectors, or length 3 vectors, such that the first coordinate is equal to the second coordinate, which is equal to the negative of the third coordinate. So that's a subspace. And we can draw that on our plot, and that just corresponds to some sort of line. It's a little hard to visualize in 3D space, but this is the set of all points that satisfy that constraint. And we can now connect this with this more formal definition that we have on the other side. So in particular, imagine that I've got some point here, x, that's in the subspace, and I've got another point here, let's say y, that's in the subspace. Well, any weighted sum of those points is also in the subspace. So the point, kind of over here, which would be, I don't know, half of x plus half of y, that's in the subspace. The point here that corresponds to 0 times x plus 0 times y, that's in the subspace. The point way out here that corresponds to infinity times x, it's in the subspace. All of these points are all in the subspace, and it coincides directly with that definition that we have over on the other side of the board. Another way of looking at this is that if we have a vector x that's in this subspace, then what we know is that we can write x as being equal to some weight a times the vector 1, 1, negative 1. Right? We know that must, okay, for some a. So if we were to fix an a, then x1 is equal to a, x2 is equal to a, and x3 is equal to negative a. So this clearly is in this subspace as the way I've written it here, but also when you look at it from this perspective, it's clear that somehow this definition of a subspace, where all weighted versions of vectors in the subspace are also in the subspace, is clearly true for this example. Does that make sense? Are there any questions? Oh, okay. So for the second example, we'll again consider n is equal to 3, and our subspace is going to be equal to the set of all points in 3D space, where x1, the first coordinate, is equal to x2, the second coordinate. So it looks kind of similar to our last example, only now we're not saying anything at all about x3. So again, we can try to draw a picture here. Here's x1, here's x2, and here is x3. And we can try to think about, well, where in this 3D space is this subspace, or what does it look like? Are there any thoughts? Yeah. That's right, exactly right. So the answer was, it looks like a big plane, a vertical plane, that's going along this diagonal between x1 and x2. All right, so to start, it could maybe like draw a line. That's the set of all points where x1 is equal to x2 and x3 is equal to 0. So I just have this line going through the horizontal plane, and I guess it goes in both directions. And then you can think about just extending that line vertically, because we don't really have any constraints on x3. x3 doesn't have to be 0. It could be anything at all. And so the vertical extension of this line is our subspace. So it's hard to draw these things. Vertical plane along the diagonal. Any questions? Okay. So again, we could consider n is equal to 3, and our subspace corresponds to all points x in this 3D space where the third coordinate, x3, is equal to 0. What would this look like? Any thoughts? Right, it's just the x1, x2 plane. So, okay, at some point these drawings are a little meaningless. But yes, it's equal to the horizontal plane. Okay, now imagine that, again, I'm in 3D space, and I'm considering the set of all points x in 3D, where x3 is equal to 5. What can you guys tell me about that set of points with respect to subspaces? Yeah. Okay, so your so the answer was that if we try to draw a picture of it, so then what we would have is the same thing as in the previous example, only now it's at a height of 5. So we'd sort of have some different horizontal plane here, but it's raised above the origin. And that is correct. That is what this set looks like. Is it a subspace? Yeah. No. Okay, why is it not a subspace? Right, exactly. So what was said is take some x that's inside, let's just call this set here, will it be confusing? Yeah, okay. Let's call this set here just curly x. So not s because it's not a subspace, it's just curly x. So now let's take some point x in that space and let a be equal to 0. So now we can say, what is a times x? Well, that's going to be just a vector of zeros, right? But that vector of zeros is not inside this set x. Okay, so here we've got an example of a set where we found a point in the set and we scaled it, and that scaled version was not inside the original set. So therefore, this is not a subspace. So it doesn't satisfy this basic definition that we have up here. And more generally, we can say a subspace always contains the origin or the all zero vector. And it has to for exactly this reason. Any questions? Oh, sorry. I already did that. Okay, one more example. And for that, I want to go back to this recommender system that we talked about before. So there, we said, imagine that we've got a matrix X, and it has, so if we look at, say, the ith row, then that would correspond to the ith movie. And if we were to look at the jth column, then that would correspond to the jth customer. And we said xij is equal to the rating of the ith movie by the jth customer. And we talked about this in the context of matrix multiplication. We said, just for the sake of argument, imagine that we can write this matrix as the product of two other matrices, U and V, where U also would say have a row for each of the different movies, but each column would mean something slightly different. So instead of representing a single actual customer, it might represent the kth genre of movies, for instance. So how much people like romance, or how much each movie is like a romance movie, or how much each movie is like an action movie. And in this matrix here, again, you would have a different row for each of our different genres. And the entries in here would say, well, for each one of the different customers, or each one of the different columns, how much does that customer like the different genres? So for a specific person, how much do they like action versus comedy versus romance? So we talked a little bit about that example. In real life, things aren't so neat and clean. This would only be approximately true, but we still just thought about this as a nice toy example that helped us understand some things about matrices and matrix multiplication. But in this example now, we can say that the span of the columns of U is a subspace. And when we write X as U times V like this, what it means is that all the columns of X lie in that subspace. So in particular, what we said was, if I were to just consider this jth customer here, so this one little column of X, then I can think about this column as a weighted sum of the columns of U, and the jth column of V tells me what those weights are. So every column in X is a weighted sum of the columns of U for some set of weights here. And this again coincides with our notion of subspaces, because the subspace corresponding to the span of the columns of U is just all the vectors that can be written as weighted sums of the columns of U. And that's exactly what X is. Well, it's a sum of them. Sum of the columns. The columns of X are some points in the subspace. It's not the full subspace, but it's some example points in the subspace. Does that make sense? Okay, so this notion of a subspace is something that's been kind of hovering around everything that we've talked about so far this quarter. We just never really talked about it in as formal of a way as we're talking about it now. But hopefully the ideas feel very natural, given the stuff that we've already covered. Okay, so the next question that I want to pose is, how do we represent a subspace? And in parallel, I want to work through an example here. Wait. Yeah, this one. So recall our earlier example where n was equal to 3, and our subspace was the set of all points x in this three-dimensional space where the third coordinate was equal to 0. That was one of the examples that we looked at before. So this is one way of representing this subspace, right? I'm just writing down the fact that the subspace contains all points where the third coordinate is 0. And for this example, that's totally valid and very simple to express. But in the context of, say, our recommender system, it's very hard to figure out what all those constraints might look like, right? And so it might be hard to take an arbitrary matrix of columns that lie in a subspace and write down an expression like this. So we want something that's going to make it a little bit easier for us to actually do machine learning. And so that's why we're asking this question. So one thing that you could do is you could say, we could represent it as the span of a set of vectors. So in this context here, we could write that S is equal to the span of two vectors. Let's call them 1/2, 1/2, 0, and 1/2, negative 1/2, 0. Okay, so there's two vectors, and I can represent any vector with the third coordinate as 0 as being a weighted sum of these two vectors. Okay, so that's A. And this is A. In fact, I could even augment that. I could say we also have 1, 0, 0, and 0, 1, 0. It's a span of all of these vectors. But this is a little bit redundant, right? I don't really need all of these vectors. I don't need 4 different vectors to represent a 2D plane. Everything I need to know about the subspace is in the span of these two vectors or in the span of these two vectors. So this is sort of overkill. So the second option that we have is that we represent S as the span of a set of linearly independent vectors. And so, in this example, that would correspond, for instance, to the span of 1/2, 1/2, 0, and 1/2, negative 1/2, 0. Okay, so these are linearly independent. We no longer have overkill. And when we do this, this is called a basis. So any set of linearly independent vectors whose span is the subspace that we care about, and that's called a basis for the subspace. There's lots of bases for the subspace. It's not unique, but for it to be a basis, the columns have to be linearly independent. And then finally, we could represent S as the span of a set of orthonormal vectors. Okay, so what do we mean by that? This means the ortho means that the vectors are orthogonal to one another. And normal means, does anybody happen to know? Yeah. Yes, they have norm, or in this case, length 1. So let me just flesh that out a little bit, and then we'll work it out in our example. Give me a little more space here. So recall two vectors, let's say u1 and u2 are orthogonal if what? What has to be true about them for them to be orthogonal? Right, their inner product is 0. So u1 inner product u2, which we can write as u1 transpose u2, and which is the same as u2 transpose u1, that has to be equal to 0. And the intuition is that these two vectors are at a right angle to one another, or perpendicular to one another. And then a vector, let's say vector u is normal if its length is equal to 1. So that is, we write this as this norm. In this case, it's also equal to the norm squared, and that's equal to the inner product of u with itself, or u transpose u. All of these are the same. They have to be equal to 1. Okay, so if we've got a set of vectors, u1, u2 through up, it's orthonormal. If I can take the inner product of two of them, ui and uj, and that inner product has to be equal to what? So there's going to be two choices. One, if I is equal to j, and the other, if I is not equal to j. So if I is equal to j, what is this inner product? 1, because they are normal. And if I is not equal to j, what's the inner product? 0, because they are orthogonal. So the set of vectors is orthonormal if their inner products with different ones is always 0, so they're all perpendicular to one another, but if they all have length 1. So if we've got a set of vectors like that that are orthonormal, and their span is a subspace, then we call this, well, there's 3 different names. There's orthogonal, or I'm sorry, orthonormal basis. That's maybe the most precise, but you often see people also calling it an orthogonal basis or an ortho basis. And when they use these second two terms, it doesn't explicitly say normal, but for many people, they treat that as implied. So just something to be aware of. If they say orthonormal, then there's no question they're orthonormal. If they say orthogonal basis or ortho basis, they might somehow be implicitly suggesting that it's orthonormal and they just didn't say it exactly. Oh, but let's keep this here. So in the context of our running example over here then, I could try to find an ortho basis for this subspace. I could write it, for instance, as the span of two vectors that are orthonormal. Any suggestions of what I could choose? Yeah. 1, 0, 0, and 0, 1. Right. 1, 0, 0 and 0, 1, 0. So here are two vectors. They both have length 1. Also, if I were to take the inner product of them with each other, that is 0. They are perpendicular to each other. And hopefully, these ideas are consistent with your intuition, your geometric intuition of what's going on here, right? We said that this was equal to the horizontal plane through the origin. So if I just wanted to tell you where something is in the horizontal plane, all I have to tell you is the x-axis and the y-axis, right? The x-coordinate and the y-coordinate. And this ortho basis is basically reflecting that same information, right? So in other words, if I have some point x in this subspace, then I should be able to write it, that point, as equal to a times 1, 0, 0 plus b times 0, 1, 0, which would be a, b, 0 for some weights a and b. Whoops, some a and b. So a and b are basically telling me the coordinates of my point in this horizontal plane. Make sense? Okay. So some of the language is a little abstract, but the concepts, hopefully, are pretty accessible. All right, so I just want to say a couple of more words about that example here. And in particular, if I've got a subspace S that I can write as the span of a collection of vectors, let's say U1, U2 through UP, where those vectors are orthonormal, then I can form a matrix U, where the columns of that matrix are these vectors. So U1 is the first column, U2 is the second column, UP is the pth column, and we call that a basis matrix. And we also say U is an orthogonal matrix. And orthogonal matrices have some nice properties that make it easy to do things in machine learning, which is one of the reasons we're going to talk about it. And one of those properties is the following. So if I were to multiply this matrix U transpose times U, let's think about what that would look like. So let's just call that product C. So then, if I were to take that matrix C and think about the ijth entry of that matrix, how can I think about that entry in terms of the U's? You might remember this comes from like the inner product representation of matrix multiplication. Yeah. Right. So this would be the inner product of the ith row of U, ith column of U with the jth column of U. And so if this is really an orthogonal basis, then just like we had before, this inner product is either 1 if I is equal to j, or 0 if I is not equal to j. And so what does that tell me about this overall matrix C? What would it look like, given this expression here? Yeah. It's exactly the identity. So all the diagonal entries, which would correspond to CIIs for some I, would be 1, and everything else is 0. So this is an identity matrix. So U transpose U for an orthogonal basis matrix is always the identity. And that turns out to be super helpful for fast calculations in machine learning. So we're going to see that in action soon. And also, another property is that U is squared length preserving. So what do I mean by that? Well, let's imagine that I've got some vector v that is a length p vector. And then let's consider the product u times v, where u is one of these orthogonal matrices. And in particular, let's think about how long that vector is. So this squared Euclidean norm. So this is equal to uv transpose times uv. And when we take the transpose of the product, then that's equal to the reverse order product of the transposes. So this is v transpose u transpose times uv. Now, can I simplify this further? What can I do from here? Right, we just proved that u transpose u is equal to the identity. So therefore, this is equal to v transpose v, or in other words, it is the length of v squared. So when we take any vector and multiply an orthogonal matrix by it, then the squared length of that product is equal to the squared length of the original vector. Okay, so that's kind of handy. Sorry, there was something else I wanted to mention, and now I'm not finding it. Ah, okay. So one last little piece of vocabulary. The dimension of a subspace, which we would write as dim. Hopefully from the examples, which I've erased now, it's not going to be too unintuitive. So when the subspace was a line, then we can think about that as a one-dimensional object. So the dimension of that line subspace was 1. When we had subspaces that corresponded to planes, 2D planes, well, the dimension was 2. More broadly, the dimension of the subspace is going to be equal to the number of vectors in the subspace or a subspace basis. So up here, for instance, we had this horizontal plane example. All the points were in 3D, but because we constrained the third coordinate to always be equal to 0, and so we were just in this horizontal plane, we only needed 2 basis vectors, even though we were in 3D space. And so the dimension of that subspace is equal to 2. If my subspace is equal to the span of the columns of some matrix, let's say X, then the dimension of the subspace is the same as the rank of the matrix X. So we talked about rank as corresponding to the number of linearly independent columns in a matrix. Maybe that seemed a little bit abstract, but now we can start thinking about it in terms of these subspaces. And we're thinking about like how big or complex are these subspaces. So a line is somehow a much less complex object than a plane. I can describe to you where I am along a line by telling you just one number. If I want to tell you where I am in a subspace, I have to give you in a plane, I have to give you 2 numbers, etc. And the dimension of the subspace corresponds exactly to the rank of a matrix X, where somehow the subspace corresponds to the span of those columns. Any questions? Okay. So I want to talk about an issue that showed up on Piazza with a lot of back and forth with the TAs, which is the following. We've got a matrix X that we said was n by p, n rows and p columns. Sorry, maybe I'm not phrasing this correctly. Just give me a quick second. What we said was that R, which we wrote as the rank of X, had to be less than or equal to the minimum of n and p. So for this discussion, let's just assume that n is bigger than p, bigger than or equal to p, like we've been doing for most of our work on least squares. And so what this implies is that R is somehow less than or equal to P. And the question arose on Piazza, well, why does R have to satisfy this? Why can't I have more than n, say, linearly independent vectors in an ND space? So can we have more than n linearly independent vectors in Rn? And what was stated on Piazza and in the notes is no, we cannot, but we didn't really go into why. So let's just talk about this question in the context of everything that we've covered here today. So in particular, the first thing I want to note is that Rn is a subspace, right? It contains the origin. It contains things at infinity in all directions. If I take any vector of real numbers, any two length-n vectors of real numbers, all of their weighted sums are also length-n vectors of real numbers. So it's an example of a subspace. Maybe not a super interesting one, but it is a subspace. And it has a basis. So a basis of Rn could equal the set of vectors. And I'm going to introduce a little notation here. E1, E2 through En, where Ei is the vector of all zeros except for a 1 in the ith location. So for instance, in 3D, it would be like 0, 1, 0 is equal to E2. Or another way of thinking about this is that this is the ith column of the identity matrix. That's n by n. And people will sometimes call this the ith canonical vector. Okay, so for any length-n vector, I can write it as a weighted sum of these canonical vectors. Right? So if I've got a point x with entries A, B, C, and D in 4D, then I can write this as A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0 plus D times 0, 0, 0, 1. Right? I can represent any point in terms of these canonical vectors. They're just telling me what the individual elements are one by one. Very simple way to represent a basis for all of Rn. And now what we're going to do is we're going to use this to show that we can't have any more linearly independent vectors in Rn. So we've already got a set of n of them, E1 through En. There can't be any more. Okay. So is there a vector V so that, all these vectors are length-n vectors, so that E1, E2 through En and V, all of those vectors are linearly independent. And so I've told you that the answer is no. And the reason is because we can always take V and write it in terms of the E's. So no matter what V is, we can write it as V1 times E1 plus V2 times E2 all the way to Vn times En. So it is already a weighted sum of the En's, and so it cannot be linearly independent from all of the E's. And so once we've got n linearly independent vectors in an n-dimensional space, we're done. There's no room for any more linearly independent vectors. All right, so if that felt a little too hand-wavy for you, you can also see the Boyd book, section 5.2, and he's got a more formal proof of this fact. But hopefully this just gives you a little bit more of a feel or intuition for why this has to be true. Okay. Are there any questions so far? No? Okay. Okay, so the final main concept that I said I wanted to cover today was projections. Okay, so the projection of a point y onto a set is simply the point in the set that's closest to y. So I might have a set of different points here. This is my set. And then I've got my point y, which is not in the set. And the point in the set that's closest to it, that is the projection of y onto the set. Very simple, very elementary concept. But now what we can do is we can say, well, what does this mean for less weirdly shaped sets, or sets that correspond to things like subspaces? Well, first let's just write this a little bit more mathematically. Y hat, which is how I'm going to write the projection of y onto the set, let's say x, and I'm going to write that as p subscript x of y, so the projection of y onto x. This is like saying, I want to find the argument x, or the point x in this space that minimizes the distance between y and x, which is the same as minimizing the squared distance. So this is just writing, as an optimization problem, the definition of the projection. Okay, so now what we want to do is understand this notion in the context of things like subspaces and bases. So we're going to hopefully tie it all together here. Let me just make sure I'm staying on task here. Okay, so in particular, let's imagine that this set X is a subspace spanned by the columns of some matrix X. In this case, that's n by p, with linearly independent columns. Okay, so now let's consider the projection onto this set. So any point in this set X is going to have the form, let's just call it y hat. It's going to look like a weighted sum of these columns. Oops. So now when we talk about a projection and we say we want to find the point y hat that's as close as possible to y in this subspace, we know that y hat has this form, and so really all we have to do is to find the weights, the w's. So what we can do is we can say, let's let w hat be the argument vector of weights w that minimizes the distance from y to xw. So now instead of explicitly searching over points in the subspace, we're just going to explicitly search over weights and use those weights to represent different points in the subspace. And then once we have w hat, y hat is simply x times w hat. Okay, but now maybe things are starting to look, hopefully, a little bit familiar. So what kind of problem is this? This is least squares, right? And what's an expression for w hat? What did we say is the least squares weight vector? We had an expression for it. Yeah. That's exactly right. We said w hat is x transpose x inverse times x transpose times y. And so now y hat is just x times w hat. So it's x times x transpose x inverse x transpose times y. And we've got this matrix in here with all these x's. And this is called a projection matrix. And we write it as P, and then with the capital X. That's the projection matrix. So this is simply Px of y. And this is a general form. It shows up in all different kinds of settings. And we can say a couple of things about it. So first of all, Px is square. So we're taking a vector y that's length n, and we're mapping it to a new vector y hat that's also length n, right? We're changing from original labels to predicted labels via this projection matrix, but we still have to have the same number of labels. So Px is always a square matrix. And in addition, Px is equal to Px squared, and by that I just mean Px times Px. And hopefully that doesn't seem too foreign either. So imagine now that I have here my subspace calligraphic X, and I've got a point y that is not in the subspace. So we're saying find the point in the subspace that's as close as possible to y. This is the same picture that we've been drawing. So here is y hat. It is simply the projection of y onto this subspace. And once I've projected y onto the subspace, my new y hat is in the subspace, right? Just by definition, that's what I was trying to do, is I was trying to find a point in the subspace. So now if I take this new point and try to project it onto the subspace, it doesn't do anything, right? Nope, lost you. Okay, so if y hat is inside the subspace, then if I try to take y hat and find its closest point in the subspace, well, since it's already in the subspace, its closest point in the subspace is itself. It's just y hat. So I can take a point and project it into the subspace and then do it again and again and again. But after that first step, nothing changes. I'm already in the subspace. Okay. All right, so there's just one last thing that I want to mention. I want to talk about these projection matrices in the context of orthogonal bases, or orthonormal bases. Are there any questions? Don't hesitate. I'll tell you, after every class, I get all kinds of people lining up asking great questions, and I'd be happy to answer them in class so that everyone can hear them. Don't be shy. Okay. So imagine that we're in this same setup. We've got this matrix X of features. We've got n samples and p features. And we also have this vector of labels y. And then imagine that I've got a basis matrix U. So it's a basis or orthobasis matrix for the subspace spanned by the columns of X. So in other words, the span of the columns of U is equal to the span of the columns of X. So we're still dealing with exactly the same hyperplane. But the issue is, or the distinction, is that before I might have had here x1 and then another one x2. These are not orthogonal to one another. They might have very different lengths even. And I'm interested in coming up with orthogonal vectors. So let's say here I've got u1 that has length 1, and then another one that's sort of at a right angle to it, u2. And they're sort of spanning the whole space. So I can write any point in this space. I can write it as w1 x1 plus w2 x2. But I could also write it using other weights. Let's say w tilde 1 times u1 plus w tilde 2 times u2. Any point in this subspace can be written as a weighted sum of the x's or a weighted sum of the u's. Okay, so they're representing the same space. The difference is that the columns of X might not be orthogonal and they might not be normalized, but the columns of U are orthogonal and are normalized. So now we could write y hat as being, it's some x times some w hat, right? It's a weighted sum of the columns of X, but it also is a weighted sum of the columns of U. So we could write this as u w tilde, for instance, right? So there exist, let me see, let me write it this way. For any y hat, there are both the w hat and the w tilde. Those two vectors both exist so that y hat is equal to xw hat, and that's equal to uw tilde. And that's for any y hat in the subspace. So now instead of doing least squares to learn w hat, I can use least squares to find w tilde. All right, let me give myself a little space to do this. So we're saying w tilde is now the argument that minimizes over all possible w's the distance between my true labels y that I care about and uw. So instead of worrying about xw, I worry about uw. So far it's not really clear why I care about this, but I can use the same formula as before, only for u instead of w. So now I've got u transpose u inverse u transpose times y. That's my w tilde. Or, in other words, y hat now is equal to u transpose u inverse, u transpose y. And this is exactly the same, with no difference whatsoever, as x times x transpose inverse x transpose times y. So this is the projection onto the span of the columns of x, and this is the projection onto the span of the columns of u, but these two things are exactly equal to one another. So if they're exactly equal, why did I do all this work? That's what you were thinking, right? Yes? That's right. It's all about the computation. So if I think about u times u transpose u inverse, u transpose, well, when this u corresponds to an orthobasis, I know that this is equal to an identity matrix. And you might recall from last week that the inverse of an identity matrix is also the identity matrix. So what this means is that this thing up here is simply u times u transpose. I no longer have to invert a matrix. So if this matrix x transpose x is big, inverting it can be really difficult to do. It can require more memory than your computer has when you're doing large-scale machine learning problems. But if you can find an orthobasis u for that same space, then you can get the exact same solution, the same predicted labels y hat, but without computing any matrix inverse. And so this notion of projection is very helpful because it helps us see that even though we derived this formula in terms of our original features x, we don't necessarily have to do exactly this computation in the computer. So mathematically, we've come up with something that's equivalent. There's no real advantage, but computationally, there could potentially be a huge advantage. Okay, so that's it for today. Next time what we're going to do is we're going to say, all right, once I have x, how do I come up with this u in the first place so I can use it? All right, thanks very much, and I'll see you all Monday.